So good morning, everybody. So this is the first lecture of this series of lectures. Okay, so we plan to give 4 lectures on the basics of matrix theory and adjacency matrices. Okay, um, so for this short-term course, we assume a basic course on graph theory and linear algebra and a little bit of probability. Okay, so nevertheless, whenever it is needed, you will try to recall whatever you have studied. Okay, so my main aim is to introduce most of the basics of the matrix theory routines. Like I will introduce Ferrand-Robinius theorem. I will talk about the spectral theorem for symmetric matrices and interlacing inequalities for eigenvalues of the symmetric matrices, and then variational characterizations and how to use them in spectral graph theory. Okay, precisely in terms of adjacency matrices of graphs, how to use them. Okay, so first I will recall the basics of graph theory. Okay, just it's a kind of recap. So for us, throughout this lecture series, graph means graph consists of 2 data. One is vertex set and the other one is the edge set. So vertex set usually is denoted by V of G and the edge set is usually denoted by E of G. Okay. The V of G stands for the vertex set, E of G stands for the edge set. So vertices are usually denoted by some dots, and the edges between the vertices are denoted by some lines joining them. Okay. Let us see some examples. Okay. Okay. So one more thing, throughout this lecture, our graphs are almost in all lectures. Vertex set is finite. Okay. V of G is a finite set. Okay. And the graph is undirected. By undirected, I mean you don't have any multiple edges, no loops. Sorry, undirected means you don't have any direction. Okay, so no direction to the edges, no direction for the edges, and simple. Okay, simple means you don't have no loops and no multiple edges. So between any 2 vertices, you will have at most 1 edge. Okay, and from a vertex to itself, you don't have any edge. Okay, so these are all the standing assumptions for this for this entire lecture series. Okay, let us see some examples. Okay, so this is the first one is a graph on 6 vertices. This is called the cycle graph. Okay, so cycle graph on 6 vertices. So here you are arranging the vertices, 6 vertices here. They are arranged in a circular order, and you draw an edge between two consecutive vertices. Okay, so in this way you draw. So here V of G is A, B, C, D, E, F, and E of the edge set is E1, E2, E3, and so on up to E6. Okay, this is called the cycle graph on 6 vertices. And then we see the click graph. Okay, the click graph is a graph on n vertices in general. Okay, in which any 2 pair of vertices are adjacent. Okay, so whenever you have 2 vertices, both the vertices should be adjacent. This type of graphs are called complete graphs. And there is a name for it. It's also called clicks. Okay, this is complete graph. Okay, this is also known as click. Okay, and then we'll see path graph. Okay, so path graph is like you arrange the vertices of the graph in a linear order in this way. Okay, and then just connect the consecutive vertices. Okay, except the first and last one. So for example, 1, 2, 2, 3, 3, 4, 4, 5. You connect the consecutive things. Okay, this is known as the path graph. And star graph is a graph in which you keep a vertex in the center and keep the rest of the vertices around the center. Okay, and then connect the center vertex with the the vertices which are sitting in the outer line. Okay, this looks like a star, so it is known as the star graph. Okay, so wheel graph is a general version of star graph we can think of. In the star graph, just connect in the outer layer also. You connect the vertices which are sitting consecutively or which are sitting next to each other. Okay, so this is known as the wheel graph. Okay, and then let us see 2 more examples. You say a graph is bipartite. Okay, so bipartite in general, the definition for bipartite is given the vertex set, you can bipartition the vertex set. Okay, such that if you take any edge, okay, let us say E is in the edge set of your graph G, then if E is of the form, let's say UV, then one end should be in the one side of the partition, the other end should be in the other side of the partition. Okay, So when I say bipartition, that means that V1 intersection V2 is also empty. Okay. So in other words, whenever I take an edge, that edge should have one end in V1, the other end in V2. Okay. So if a graph admits this type of bipartition, we call the graph as a bipartite graph. Okay. So in the above, I have given two examples of bipartite graph. In these examples, the first graph, if you see the vertices 1, 2, 3, 4, this form one side of the partite set, and 5, 6, 7, this forms the other side of the partite set. Okay. And that is a special class of bipartite graph, which are called complete bipartite. By complete bipartite, we mean so you are able to bipartition the vertex set into two parts such that any two vertices, okay, such that one in V1, the other in V2. Okay, so you can call this part as okay, so this is V1, this is V2. So any pair of vertices such that one in V1, other in V2 have an edge. Okay, so this is called complete bipartite. Okay, so we will use all these notions, all these examples in our lecture now. Okay. Okay, so far so good. So the main idea of spectral graph theory is study the structural properties of the graphs by associating various types of matrices with a given graph. Okay. So as my title says, I'm going to talk about adjacency matrix. Okay. So adjacency matrix is an 0-1 matrix. Okay. It is a symmetric 0-1 matrix. Okay. So if it is a symmetric matrix, then it is diagnosable. You have real eigenvalues and orthonormal set of eigenvectors. So using them, we can say many things about the structure of the graph. Okay. So before introducing the notion of adjacency matrix, let us recall some more basic definitions from graph theory. Okay. So these are all typically covered in a first course. I want everybody to be in the same page. So I'm just recalling all these things. Okay. So G equal to V of G comma E of G. This is the graph which I'm working with. Okay. A subgraph H. Okay. So a subgraph H of G is a graph defined in this way. The vertex set of the graph H is okay. Vertex set of the is a subset of the vertex set of G, and the edge set of the graph is subset of the edge set of G. Okay. Just you have both the vertex set and the edge set. Both are subsets of the graph G. That's all. Okay. This is known as this is called a subgraph of G. Okay. So this is the definition of sorry. Subgraph. Okay. And we say the subgraph is spanning. This is a bit large. Okay, I think I can reduce the thickness. A subgraph is said to be a spanning subgraph if it is a subgraph whose vertex set should be equal to the vertex set of the entire graph G. Okay, this type of subgraphs are called spanning subgraph. Okay, in other words, you take a graph. In that graph, you just remove some of the edges. Okay, then whatever subgraph you are getting, those subgraphs are called spanning subgraphs. Okay, and then we say a vertex VA is incident with an edge EK. Okay, so you take a vertex VA, and we say the vertex VA is adjacent to an edge EK. If this happens, VA intersection EK is non-empty. Okay, so what is the meaning of this line? So EK it is an edge. Typically, this is a two-element subset, something like VA VJ. Okay, EJ is an edge connecting the vertices VA and VJ. So we think of this as a two-element subset of V of G. Okay, if the vertex VA is part of that edge, then we call the vertex VA is incident with an edge EK. Okay, and we say two vertices VA and VJ are adjacent if there is an edge between them. Okay, so note that this is about terminology. So some places we will denote the edge by this set bracket VA comma VJ. In some places we will denote by this open bracket VA comma VJ. Both are the same. Okay, I hope there should not be any confusion about it. Okay, and then a walk in a graph. Okay, a walk in a graph is just a non-empty alternating sequence of vertices and edges. Okay, so you just arrange the vertices and edges. Okay, alternatively, subject to the following constraint. Okay, the walk should start at end in vertices. Okay, both the starting and the ending point of the walk should be vertices. Okay, they can be anything, and then when you are keeping an edge next to a vertex V, okay, when you're keeping an edge next to a vertex V, we are going to say, what are we doing? Uh, the vertex should be part of that edge. Okay, so here V1 and E1 I'm writing next to each other. Okay, V1 E1 I'm writing next to each other. That means that V1 is part of the edge E1. Okay, so maybe if you want a example, we can see like this. You take this graph. Let's give name V1, V2, V3, V4, E1, E2, E3, E4, E5. A typical walk is I'll just give a name W. Okay, I'll start with V1 and then I can use E1 or E4 or E5. Okay, V2 and then E2. Then I can go to V3. From V3, I can again go, I can track back. Okay, I can go back to E2 and then V2, then E1, V1, V5, V4. Okay, just an alternating sequence of vertices and edges in which if you keep if you place an edge after a vertex, then the vertex should be incident with that particular edge. Okay, and the only constraint is the starting and the ending elements of this walk are vertices. Okay, and we say a graph G is connected. Okay, and a path. Okay, the next definition is path. So path is a walk in which any two vertices are in which the vertices which are belong to the walk are distinct. Okay, so in this example, if you see, I'm starting at V1. Okay, I'm up to V3. I'm just using distinct vertices V1, V2, V3, and so on. Okay, starting from V3, you see, I'm going to repeat the vertex V2. Okay, so in a path, this is not allowed. Okay, so a walk is a path in which you don't allow the vertex repetitions. Okay, you can easily convince yourself that if the vertices are not repeating, then the edges also will not repeat. Okay, so this is the definition of a path. And we say a graph G is connected. Okay, if we say a graph G is connected if between any two vertices you should have a path connecting between them. Okay, so this example, whatever I have drawn, this is a connected graph. Okay, just to make it disconnect, or we can draw something like this. If I take this as my graph, V1, V2, V3, V4, V5. If you think of this entire these two parts as your graph, then this is the disconnected graph. The reason is from V1 to V5, I don't have any V1, V5 path which connect these two things. Okay. And a component is in a graph is a maximal connected subgraph. It is a subgraph of G. Okay. So let us see this terminology. Okay. So this is a first of all subgraph of G. That is V of G is sorry this one subgraph of G. That is V of G. If I call H is a component, then V of H should be subset of V of G and connected. Okay, as a subgraph of G, it should be connected between any two vertices of H. I should have an edge. I should have an path in H itself at maximal. Okay. So adding one more vertex to this subgraph will make your graph disconnect. Okay, that is the meaning of maximal connected subgraph. Okay, this is known as a component. Okay, and the next terminology is just a minute. Okay, I'm sorry about the. Okay, I'm sorry about the interruption. Yeah, so just. A cycle is a path in which the starting and ending vertices are the same. Okay. I just learned that. I think some of you did not get the mail. Okay, maybe after the talk I will sort out. A cycle is a path in which the starting and the ending vertices are the same. Okay. Now we say a graph G is a tree if there is exactly only one path between any two vertices of the graph G. Okay. So we say this is one of the equivalent condition. Okay, in general, you might have studied a graph G is said to be a tree if it is a connected acyclic graph. Okay, so this is same as saying that one of the equivalent condition is there is exactly only one path between any two vertices of the graph G. Okay, and in a connected graph G, like between any two vertices, you will have at least one path. Okay, it may happen that you'll get more than one path. Okay, so we are going to define the concept of distance between the vertices of the graph G. Okay, this is defined in this way. You see the all possible paths between the vertices Va and Vj. Okay, and among those paths, choose a path which has minimum length. Okay, we have more than one path with minimum length. Take any path which is having minimum length, measure the length of it. That is called the distance between them. Okay, so that is typically denoted by d of Vi, Vj. Okay, the distance between the vertices Va and Vj is denoted by d of Vi, Vj. It is denoted by d of Vi, Vj. It is defined in this way. Okay, measure the distance between the length of the measure the length of the shortest path as in that. Okay, and the diameter of the graph. Okay, the diameter of the graph is the you just measure the distance between any two possible pair of vertices Va and Vj. Okay, to be specific here, I and J are not the same. Okay, no need. Even if I'm taking maximum, so even if Va equal to Vj, I don't have to worry. Okay, so the diameter is just the maximum of the distances Va and Vj. Okay, so I'm going to use all these notations in the upcoming part of the lecture. Okay, great. So are you with me so far? Just I'm recalling the graph theory part. If you have any doubt, you can yeah. I'll happy to clarify this. Okay, so if there is no doubt, maybe I will proceed. Yeah, starting from this, I think maybe many of you may not know this notion. Okay, so let us start the new definition: adjacency matrix. Okay, so as I told, the main idea of spectral graph theory. Okay, so spectral graph theory. Okay, so study the structural properties of the structure of the matrix. Sorry, of graphs. Study of structure of graphs using eigenvalues. Okay, so precisely one can study about like there are many things about connectedness, about the number of triangles. There are many things. Okay, we'll see in this course. Okay, using the spectral data, how to study these properties. Okay, so in this lecture, I will introduce the notion of adjacency matrix. As I told you previously, Professor Sasmita will talk about Laplacian matrices, and she will discuss many things about Laplacian matrices. And then Professor Satyanarayana will discuss about distance regular graphs. Okay, so that is another interesting families of objects. Okay, so let me start. So adjacency matrix of a graph G, okay, is an n by n matrix where n is the number of vertices. Okay, if it is a graph on n vertices, then we are associating an n by n matrix. Okay, whose ijth entry is given defined in this way. Okay, so Aij stands for the ijth entry of the matrix A. Okay, so Aij you keep a 1 if the corresponding vertices Va and Vj are adjacent. Okay, so to be precise, so we are associating a matrix with the graph. Okay, the matrix whose rows and columns are indexed by the vertices of the graph. Okay, so it is a square matrix. A of G is a square matrix whose rows and columns both are indexed by the vertices of the graph v1, v2 up to vn, v1, v2 up to vn. Okay, whose ijth entry, every entry of this matrix is a 0, 1 0, 1. Okay, this is a 0, 1 matrix. All the entries are 0, 1. So we are going to keep a 1 here if there is an edge between the vertex which is giving which is giving the row index and the vertex which is giving the column index. Okay, that is, if VA and VJ are adjacent, okay, if VA and VJ are adjacent, then you are going to keep 1 in this matrix in the corresponding place. Okay, otherwise you are going to keep a 0. Okay, this is how we are defining the adjacency matrix of the graph. Okay, so throughout this lecture we are considering only undirected graph. Okay, so undirected and simple graphs. Okay, so this graph, this matrix will have zeros on the diagonal. Okay, on the diagonals you will always get zeros only. Okay, there is no other choice. And then it is a symmetric matrix. Since the graph is undirected, whenever you have an edge between the vertices VA and VJ, you should have an edge between the vertices VJ and VA also. Hence the graph should be a symmetric. Hence the matrix should be a symmetric matrix. Okay. Okay, so let us see a simple example. So whatever I said here. Okay, so this is a graph on 4 vertices. Okay, V1, V2, V3, V4 are the vertex set, and the edges are, I'm not giving the name. Okay, so edges are V1, V2, V1, V3, V1, V4, V2, V3. We have 4 edges. Okay, the adjacency matrix is given in this way. Okay, let me explain just one row, and then the rest of them you can fill on your own. So see, the first. The labels or the rows are indexed by the vertices, as well as the columns are indexed by the vertices of the graph. Okay. Now you see V1, V1. Okay, the first place, that is V1, V1. So here I'm keeping a 0 because from the vertex V1 to itself I don't have any edge, since the graph is a simple graph. Okay, and look at the entry V1, V2. Okay, V1, V2, between the vertices V1 and V2 I have an edge, hence I'm keeping a 1 here. Similarly, between the vertices V1 and V3, V1 and V4, we have edges. So here and here. Hence, I'm keeping an 1 over here. Okay. So as I said, this is a symmetric matrix. Hence, I can, if I know the first, if I can fill the first rows, then I can fill the first column symmetrically. Okay. And then just I will explain this 2/4 entry. Okay. So 2/4 entry, you see the vertices V2 and V4, between them I don't have an edge. Hence, I'm keeping a 0 here. Okay, hence I'm keeping a 0 here. So similarly, you can fill the rest of the entries of this graph, this matrix. Okay. Now, so since the adjacency matrix is a symmetric matrix, so if I know the like the spectral properties of adjacency matrix, spectral properties of symmetric matrix, that means if I know how to handle these symmetric matrices, then I can use the theory to study these adjacency, this in particular this adjacency matrix. So now I'm going to discuss about the symmetric matrices. Okay, just again I'll just recall some of the basic notations. Okay. So if A is an n by n real or complex matrix, okay, the characteristic polynomial of this matrix is defined in this way. Okay, you take the determinant of A minus lambda I. Okay, so the characteristic polynomial is given in this way, and the characteristic equation is the determinant of A minus lambda is equal to 0. Okay, equate the characteristic polynomial to 0, then we get the characteristic equation. Okay. So the roots of this characteristic equation are called eigenvalues. Okay, and the fundamental theorem of algebra says that every n is missing here. So every n by n matrix, every n by n real or complex matrix has n eigenvalues. Okay, I think I have to say. Okay, so needless to say, this characteristic equation is a degree n polynomial. Hence, you can apply the fundamental theorem of algebra to ensure that it has n eigenvalues. Okay, so if it is an arbitrary matrix, then we don't know about anything about the eigenvalues and the eigenvectors. They can be complex, and you may have some deficiency in the eigenvectors also. For the symmetric matrices, that will not happen. So that's what we are going to do next. Okay. And this one more interesting property, this is not very well known. We may use in the lecture, or some other teachers may use this. Okay, for the characteristic polynomial, coefficients of the characteristic polynomial, you have a nice expression or nice formula in terms of the principal minors. Okay, so I think all of you know from first course in maybe in algebra, in theory of equations. If you know all the roots of an equation, then you have a formula for the coefficients of the equation. Okay, like like the coefficient of x power n is up to sign. You take sum of all the all the roots, and the coefficient of x power n minus 2 or lambda power n minus 2 is up to sign. You take the sum of the products of the roots taken 2 at a time, and so on. Okay. So for characteristic polynomial, then we do have one more interesting formula. Okay. So let me explain this terminologies first. Okay. The first thing is submatrix. Okay. So I guess all of you know what's the submatrix. Okay. So I'm having a matrix. So if A is a matrix, okay, just you take the sum of the rows and the sum of the columns. Okay, maybe you can take some I1, I2, some Ik rows, and then J1. Okay, right here, J1, J2, JS columns. Okay, the matrix whose entries are taken from like I1, I2, I3, Ik, and J1, J2 up to JS. Okay, which are sitting in the intersection of these things. You extract all those entries, then you will get a K by S matrix. Okay, that is called just a submatrix. Okay, so this is that is just called as a submatrix. Okay, submatrix can be formed in this way. Okay, for the principal submatrix, sorry, just a minute. Oh, I'm sorry. Okay. Okay. So what I was explaining. Okay. So submatrix I explained here. What is the principal submatrix? For principal submatrix, so if you take I1, I2, Ik rows, then you have to choose the same columns, I1, I2 up to Ikth column. Instead of J1, J2, JS, you choose the this. Maybe I can write like this. Ik. This should be both for rows and columns. Rows and columns both are indexed by the set I1 to Ik. These are all called principal submatrices. Okay. So by the definition, principal submatrices are square matrices. Okay. So now I think it should be clear what we have done. Principal submatrix. Okay. It's a square submatrix. Okay, whose rows and columns are indexed by the same set of index, same index set. Okay. The determinant of a principal submatrix is called a principal minor. Okay, the principal minor, the definition of principal minor is it's the determinant of the principal submatrix. Okay, so now let us give a notation. The notation Ek of A stands for you take all possible K by K principal subminors, okay, and sum everything. Okay, so for if you take a subset consists of K elements, okay, you look at the corresponding principal submatrix, calculate its determinant, okay, that is the principal minus corresponding to that K by K principal submatrix, okay, and you can vary this K element set, okay, so you will get n choose K subsets, okay, you just take sum of all these principal minors, you give a name Ek of lambda, Ek of E. Okay, so the characteristic polynomial of the matrix admits this nice form. Okay, so the characteristic determinant of A minus lambda I, maybe this should be lambda I minus A. Just take care of it. Okay, not A minus lambda I, lambda I minus A. Otherwise, I may have a minus over here. Okay, so this is the coefficients of the characteristic polynomial are given by this. For lambda, the coefficient of lambda power n minus 1, that is E1 of A up to sign. Okay, so E1 of A, what is E1 of A? Take the sum of all 1 by 1 principal submatrices. What are the 1 by 1 principal submatrices? The 1 by 1 principal submatrices are, you look at the matrix, I had to choose a row, okay, and I had to choose the same column. Okay, then what does it mean? Just looking at the diagonals. Okay, that is, you just take sum of the all diagonal entries. Okay, that is also, you know, trace. Okay, trace is the coefficient of this lambda power n minus negative of the trace. Okay, for the second one, You just take for second one, I mean like this lambda power n minus 2. You look at the E2 of A, just look at all possible 2 by 2 principal minus, sum everything, you are going to get it. What about the last term? What is the n by n principal minor? It has only one n by n principal minor, that is the entire matrix itself. So En of A is nothing but the determinant of your matrix. Okay. So I'm not going to give a proof of this thing. Okay, the proof you can found in Hahn and Johnson's book. Okay, I will give you the references at the end. Okay, let us see some examples. Okay, by examples I mean let us take some graph and let us try to calculate the eigenvalues of those graphs. Okay, see, note that it is so we are associating a matrix with a graph, and our plan is to study the structural properties of the graph using the spectral data. Okay. First of all, calculating eigenvalues of all the graphs is not an easy task. Okay, in fact, you can't give an analytic method to calculate eigenvalues of all the graphs. Okay, so nevertheless, for some of the families of graph, one can do these things. Okay, so I plan to revise all the matrix theory facts. Okay, so before recalling, so to do this calculation or computation, I need to assume some amount of matrix theory. Okay, so I will just recall and tell. Okay. I'll recall and use. Okay, so the first thing is let us look at the complete graph on n vertices. Okay, so I'm going to look at the complete graph Kn. Okay, let us calculate the eigenvalues or the spectrum of this. Spectrum means the set of all eigenvalues with including their multiplicity. Okay, how to calculate all the eigenvalues of the complete graph. Okay, so complete graph like K5 we have seen already. So this is a graph on n vertices. Okay, in general, it's a graph on n vertices such that between any two vertices, you have an edge. Between any two distinct vertices, you have an edge. That's the definition of our complete graph. Then, what is how the adjacency matrix of complete graph look like? So this is a graph in which, for every simple graph, we have the diagonals are 0. Okay, and rest of the entries everywhere you keep 1. Okay, because between any two vertices you are getting an edge, so everywhere you will get 1 except the diagonals. Okay, so if I had to calculate the eigenvalues of Kn, I should know what are the eigenvalues of this matrix. The eigenvalues of this matrix can be calculated explicitly. Okay, so let us consider this matrix all ones matrix. Give a notation. This is the standard notation. J stands for all ones matrix. Okay. What are the eigenvalues of this matrix? Eigenvalues of J are spectrum. Okay. So this is a rank 1 matrix because everywhere you have 1. So every row is a linear multiple of each other. So this is a rank 1 matrix, and rank 1 symmetric matrix is the number of 0 eigenvalues should be equal. Number of non-zero eigenvalues should be equal to the rank of the matrix. Okay. And the row sum is constant. Every row sum is equal to n. So if the row sum is constant, then that row sum should be an eigenvalue. The reason is, if you take these all one vectors, okay, all ones vector, E is or E transpose is the row vector all ones, then JE you will get n into E. Okay, so eigenequations are satisfied. Eigenequation is satisfied. Hence, E is an eigenvector with eigenvalue n. Okay, so and it's a rank 1 matrix. So n is the only non-zero eigenvalue with multiplicity 1. Okay, so in the bracket 1, whatever I am writing, this means that multiplicity of the eigenvalue. So, I mean this line. So n power this bracket 1, that means that n is an eigenvalue with multiplicity 1. Okay, and what are the rest of the eigenvalues? This is a rank 1 matrix. So rest of the eigenvalues should be 0. So 0 has multiplicity n minus 1. Okay, and in the first course in linear algebra, you might have seen that if you know the eigenvalues of a matrix A, okay, maybe X is a matrix, you know all the eigenvalues of this matrix. And then if you have to just add identity to this matrix, then you don't know all the eigenvalues of this matrix, X plus I also. Okay. You have to just add 1 to it, all the eigenvalues of X. Okay. So here, the adjacency matrix of complete graph, okay, this is nothing but J minus I. Okay, all ones matrix minus I. So using this, I can explicitly say what are the eigenvalues of, or the spectrum of, or spec of A of Kn. Okay, This is the notation I'm using, spec of A of Kn. This is the spectrum of this matrix A of Kn. So n minus 1, because n is an eigenvalue with the multiplicity 1. N is an eigenvalue with the multiplicity 1 for j. So minus 1 I had to add. That is n minus 1 with the multiplicity 1. And from 0, I had to subtract 1. So minus 1 with the multiplicity n minus 1. Okay. So these are all the eigenvalues of the complete graph. Okay. Is it clear? This is one of the routine example in calculating the spectra. If you know the complete graph, you know all the eigenvalues of the complete graph. Okay. So now let us look at the next problem. That is a complete bipartite graph. Okay. So I think you remember what is complete bipartite graph. You have partitioned the vertex set into two parts. The one side you have p vertices. The other side you have q vertices, and then you are joining everything, all possible edges between these things. Okay. Everything is connected. So now you can calculate the eigenvalues of KPQ. The KPQ is the notation for the complete bipartite graph. Okay. So what is the adjacency matrix of PQ? So now you have to fix the ordering in a neat way. Okay. So what is the order you want to keep? So just to place all the vertices of the one of the partites at first, and then keep the rest of them next. Okay, V1, V2. So look at the matrix between the vertices of V1. That is, if I take if I focus on this part, okay. So here everywhere I'll get the zeros only, because from the vertex of V1 to itself, you don't have any edge, hence you are going to get zero matrix in this block. Okay, this is a block matrix. The vertex set of KPQ I'm partitioning into V1 union V2. Okay, between the vertices of V1 to itself, you don't have any edge, hence you are keeping a zero there. Similarly, from V2 to V2, you don't have any edge, so you are going to keep a zero there. Okay. What about V2 to V1? Between all the vertices of V1 and V2, you do have an edge, hence you are going to keep all ones matrix. Okay. J stands for all ones matrix. And so unlike the previous J, that J was an n by n matrix, here this J is a P by Q matrix. Okay. Where P is the cardinality of V1 and Q is the cardinality of V2. Okay. The number of vertices, then n equal to P plus Q. Okay. Now let us work on the eigenvalues of let us calculate the eigenvalues of this graph. Okay. So A of KPQ, first observation is, what is the rank of this matrix? So you see this block, you look at this matrix up to this point, this level, okay, or the rows corresponding to the vertices of V1. What are you getting? Every row is a linear multiple of the other rows. Hence, the rank of this part up to V1, you are going to get rank is equal to 1. But similarly, for the rank corresponding to the second part corresponding to the rows of V2, you are going to get rank 1. Okay. So this is a rank 2 matrix. Okay. So rank of this matrix, rank is 2. Okay. And note that the trace of this matrix, okay, trace, that is the sum of the diagonals, that is equal to 0. We do know trace is equal to the sum of the eigenvalues. So trace is equal to 0. It is a rank 2 matrix. Okay. So if lambda is a non-zero eigenvalue of it belongs to the spectrum of APQ, AKPQ, then minus lambda should be also in the spectrum. Because lambda is the only non-zero, if lambda is a non-zero eigenvalue, then sum of the eigenvalues I'm going to get 0. So negative of lambda also should be also an eigenvalue. Okay, it's a rank 2 matrix. So if lambda is a non-zero eigenvalue, then minus lambda is also an eigenvalue. So it is good enough to calculate what is my lambda. Okay. So how to do that? There are many ways to do that. So one thing is, maybe I can explicitly tell you. So before that, one small observation. What is the number of edges in the complete bipartite graph? Number of edges in KPQ is PQ. Okay. Product rule of combinatorics, if you apply, we are going to get a PQ number of vertices. Okay. Then, so the matrix for the matrix, I have given something. Okay. For the coefficients of the characteristic polynomial of matrix, I have given some expression. If you see this, the n minus kth coefficient is just to take the sum of all principal minus of order k. Either you can use it. If you use it, you will get it. Okay. Otherwise, you can do an explicit calculation. Maybe I will do that. I think I found somewhere this proof. Maybe let me recall that. Okay. So let us take instead of writing a of kpq, I'll just write a only. Okay. Ax equal to, let us say, lambda x is the eigen equation. Okay. So let me give a name for the eigen entries of the eigenvector. X1, xp plus 1 to xp plus q. Okay. So ax equal to lambda x will give me. So look at the first row and multiply with this vector x. Okay. X transpose we keep here. I'm going to get xp plus 1 up to xp plus q, that is equal to n. Okay. Maybe I will write xp plus q. This is equal to lambda times x1. Okay. Similarly, corresponding to the second row, the same thing, xp plus 1 to xp plus q. This is equal to lambda times x2. For the first p equations, okay, I'm going to get the same thing. Okay, p is the number of vertices in the first part. What will happen to the second part? The vertices corresponding to the v2 part. J into the first p elements of the vector x, that is x1 to xp, which is equal to lambda into xp plus 1, and x1 up to xp, which is equal to lambda into xp plus 2, and so on up to x1 plus up to xp, which is equal to lambda into xp plus q. Okay, you have two different set of equations. Okay, here I have p equations, everything is the same, and here I have q equations, and everything are the same. Okay, now I have to cleverly manipulate this equation to find out what is the lambda. Okay, so remember, I know like p plus q minus 2 eigenvalues. Okay, so what are the p plus q minus 2 eigenvalues? Note that it's a rank 2 matrix, rank 2 symmetric matrix. That means that it has exactly 2 non-zero eigenvalues. From here itself, I have that 0 is an eigenvalue with multiplicity p plus q minus 2, that is n minus 2. So I have to calculate only the 2 non-zero eigenvalues. For that also, I have one more constraint, that is that some of these eigenvalues are equal to 0. Hence, if I know one eigenvalue, then I can take the other one. Okay. So from here, if I can compute this non-zero eigenvalue lambda, that is good enough. Okay. So here the simple thing is, you see here, x1 plus x2 up to xp is equal to x1 plus x2 up to xp is equal to lambda xp plus 1. Okay. Now look at the first p equations. Just trying to connect these two equations. Okay. So you sum first p equations. Okay. Sum first p equations. What do you get? The right hand side in all the equations, I'm getting the same thing. So p times xp and so on. This is equal to lambda into the right hand side. I'm adding all these things. Okay. Now what can I do? But this quantity, what I'm equating here, this is equal to lambda into x1 plus x2 up to xp, that is given by lambda into xp plus 1, right? That is lambda square into xp plus 1. So here what I'm doing in this part, what I'm doing in this line, what I'm doing, just to add first p equations. Okay, the left hand side of all these p equations are the same, hence I'm going to get p times xp plus 1 to p xp plus q. Okay, that is equal to lambda into, just sum the right hand side, right hand side I'm getting x1 to x2 up to xp. Okay, but x1 plus up to xp, that is given by, from the second group of equations, I'm getting lambda into xp plus 1. Okay, so what I can do now, I have to get rid of this xi somehow. Okay, that's the only aim. So what I will do, I will I can take sum of these equations for q times. Okay, so at the end, what I will get this will implies lambda square minus pq is equal to 0. That's what I will get. Okay, maybe I can write this little below. So how to achieve that? Insertion. So here I have q equations. See, now like I will do it, I will repeat, I can do the same thing, right? So p into xp plus 1 up to xp plus q. So lambda into, this is equal to lambda into, instead of lambda xp plus 1, I can use the second equation to get xp plus 2, right? So I can get this is equal to xp plus 2. Okay, lambda square. And so on, p into xp plus 1, xp plus q, this is equal to lambda square into xp plus q. Okay, now what can I do? Just sum these things.
Add all these equations.
Yes, you can sum all these equations. Okay, very good. So sum all these equations, then you are going to get your required thing. Okay, so p into q into xp plus 1 up to xp plus q. This is equal to, on the other side, what you will get? Lambda square into x p plus 1 to xp plus q. Okay, now I will cancel out this xp plus 1 sum to xp plus q. Okay, why? You have to justify one thing, this sum will not be equal to 0. If it is equal to 0, then I'm not going to get anything. Okay, it is a small exercise to show that this sum is not equal to 0. Okay, that I'm giving you as an exercise. Okay, xp plus 1 to xp plus q, this should be different from 0. Okay, if it is 0, then what will happen? You just convince yourself. So hence I'm getting this equation. Okay, so now I can shift this a little more above. So this implies lambda is equal to plus or minus pq. Hence the entire spectrum of this complete bipartite graph I can calculate explicitly. So the square root of pq, this has multiplicity 1, and minus square root of pq, this has multiplicity 1, 0 has multiplicity n minus 2. This p plus q minus 2. Okay. So yeah, so in the symbol, like this, we can calculate a spectrum of some families of graph explicitly. Okay. The another family is the cyclic graph. Okay, for the cyclic graph and for the path graph, with a little effort, we can calculate all the eigenvalues. Okay, so So I'm not. I thought I will do the calculations. Now I will not do this calculation. I refer to the book Graphs and Matrices by Professor Bapat. So you can see these calculations in that book. Okay. And this complete bipartite graph, whatever calculation I did, this is not in Professor Bapat's book. You can see an alternate proof of the same thing in Professor Bapat's book. Okay. Okay. So let us move on to the main topic, the next topic, symmetric matrices. Okay. So I'll briefly recall what are all the facts we need from symmetric matrices. Okay. So an n by n real matrix is said to be symmetric. Okay. So maybe I'll stick to only real matrices for this part. An n by n real matrix is said to be symmetric. A transpose is equal to A, and an n by n complex matrix is said to be Hermitian if A star equal to A. Okay. So all the eigenvalues of Hermitian matrix or eigenvalues are real symmetric matrices are real numbers. Okay. The proof is not hard to see. Suppose if you take x is equal to lambda times x. Okay. Then you look at this quantity lambda into x with x. Okay. So of course, this is an eigenvector. Eigenvector x is an eigenvector, so it should be different from 0. So lambda into this inner product x with x. This is same as inner product lambda x with x. Okay. So this is same as, since lambda is an eigenvalue and x is the eigenvector, I can write like this. I can use the eigen equation to write this. And then using the definition of inner product, this quantity is same as, you can take A to the second coordinate, A will become A transpose, but A transpose is equal to A, hence I can put simply A there. Okay. Again, use the eigen equation here. We're going to get x is equal to lambda times x. Okay. And you can take this lambda out now. So this lambda will be lambda bar into x. Okay. So x is a non-zero vector. So inner product of x itself is different from 0. So we can cancel out this inner product x with itself in both sides. So together with so this implies that lambda is equal to lambda bar. Hence, all the eigenvalues of real symmetric matrices are real. Okay, the same argument was for complex Hermitian matrices also. Okay, so whenever you have a real symmetric matrix, all the eigenvalues are real. And we need a terminology. We say a real matrix is orthogonal if inverse of the matrix is A transpose. Okay, if A is a real matrix, we say A is orthogonal. If A transpose is equal to A transpose A equal to identity, that is equivalently the inverse of the matrix A is A transpose. Okay, similarly, you can define the notion of unitary matrices for complex matrices. The matrix A should be unitary if A star equal to A star A. Okay. So one of the important theorem in a first course in linear algebra you might have studied, the spectral theorem for symmetric matrices, real symmetric matrices. Okay, so this says that you take any real symmetric matrix, then I can diagonalize it orthogonally. Okay, that means that every real symmetric matrix can be written in this A equal to something like a U D U transpose, where U is a orthogonal matrix and D is the diagonal matrix whose diagonal entries are just eigenvalues of this matrix A. Okay. So I have included the proof in this slide. Okay. So proof by induction, this you can find in linear algebra book by Ramchandra Rao and Bhimasankaram. Okay. I just taken this proof from there. The proof for the case n equal to 1 is trivial because the 1 by 1 matrices are just the real numbers. Okay. They are it is already in the diagonal form. Okay. Backus-Leel test. So assume that the result is true for every real symmetric matrix of order up to n minus 1. Okay, exactly n minus 1 is also fine. Okay, so let me take A to be any symmetric matrix of size n minus 1, n by n. Okay, now I have to show that A is orthogonally similar to a diagonal matrix. Okay. So by fundamental theorem of algebra, you know that every matrix has an every real matrix every real or complex matrix has n eigenvalues. Okay. Now just now I have shown that for symmetric matrices all the eigenvalues are real. Now pick any of the real eigenvalue of the matrix A with the corresponding eigenvector x. Okay. To make our life simple, you choose x to be a unit length vector. Okay. Now I'm going to construct the columns of this orthogonal matrix P. Okay, so P is the orthogonal matrix for which I'm going to get this uh, something like A equal to P dP transpose and so on. Okay, so first column of P is given as you choose the, or P is the first step towards constructing the orthogonal matrix. Okay, so P is the orthogonal matrix whose first column is just the eigenvector corresponding to that eigenvalue lambda. Okay, then if you do this calculation, P inverse AP, okay, P inverse AP, if you calculate, then you are going to get a matrix of this form, lambda y transpose 0 y. Okay, here this 0 you will get because of this eigen equation Ax equal to lambda x. Okay, this is a routine exercise in linear algebra. If you are not this, you can homework you can take. Okay, the useful fact here is, maybe I will write down, when you have to see this matrix multiplication, this can be thought of as the matrix vector multiplication in this way. I'll just explain what I'm writing. So B is the matrix whose columns are given by B1 to Bn. Okay, then this matrix multiplication AB you can think of as n matrix vector multiplication, AB1 up to ABn. Okay, you just use it together with your eigen equation, you will get this form. Okay, now here so P is an orthogonal matrix. Okay, and I have extended, and here also I have used one more fact, like Gram-Smith sort of things. P is an orthogonal matrix whose first column is X. Okay, that means that X is an orthonormal vector or orthonormal vector. I'm extending that orthonormal vector to a basis and then orthonormalize the rest of the entries, rest of the columns of the matrix P. Okay, so by definition, P is an orthogonal matrix, hence P inverse is equal to P transpose I have. Okay, so if so this P inverse AP, that still remains a symmetric matrix. Okay, remember, if P is an arbitrary invertible matrix, this P inverse AP need not be a symmetric matrix, even though A is symmetric. Here the way we have chosen it, we are getting this P inverse AP is also a symmetric matrix. Okay, so since this is symmetric, so the first column below the entry lambda, everything is 0. Hence, this first row should be also equal to 0. Hence, we are going to get lambda 0 0 C. Okay, now C is a symmetric matrix. For that C, I can apply the induction hypothesis. Okay, C is a symmetric matrix. It is unitarily diagonalizable or orthogonally diagonalizable. You get the matrix which you are getting for that orthogonal diagonalization. Okay, C is a symmetric matrix. I can orthogonally diagonalize it using the matrix W. So using this W, I can get back the matrix Q. This Q is the one which is going to diagonalize our matrix. Okay, Q is given by, take the diagonal matrix whose first entry is 1. Okay, and the rest of the entries in the first row are 0, and the rest of the entries in the first column are 0. Just keep the W like this. Okay, this is the meaning of this symbol, diagonal of 1 comma W. That means that keep 1 in the first place and put 0 blocks in the first row and the first column, and keep the W whatever you are getting. Okay, then corresponding to this Q, you do the calculation, not Q, corresponding to this PQ, you do your calculation. You're going to get the like proof of the spectral theorem. Okay, just I said briefly because our main aim is not to cover the proof of this. Okay, suppose if you don't know the proof, this is how the spectral theorem is proved. At least the matrix version one can easily show using the induction. Okay, so for this part you can see the book Linear Algebra by Ramachandra Rao. I think Ramachandra Rao and Bhima Sankaram. This is an interesting book. This entire book is written from the matrix theoretic perspective. Okay, so if you are teaching for BTechs, you can consider seeing this book. Okay, and one more property of real symmetric matrices, which I will use after this. If lambda 1 to lambda k are the distinct eigenvalues of the real symmetric matrix, then its minimal polynomial is given by x minus lambda 1 into x minus lambda 2 into up to x minus lambda k. Okay. That is, if lambda 1 up to lambda k are the eigenvalues, then the minimal polynomial is just the linear factors x minus lambda 1 into up to x minus lambda k. Okay. I think you might have seen for diagnosability, one of the equivalent condition is its characteristic polynomial splits linearly. Okay. So here the condition what you are doing is for symmetric matrices. Okay. I'm saying just only the one part. If you have a real symmetric matrix and if lambda 1 to lambda k are the distinct eigenvalues, then the minimal polynomial is just the product of the linear factors given by the distinct eigenvalues. That's all. The proof is not hard. Okay, just you can so use the spectral theorem. Okay, most of the once you know the spectral theorem, then everything about the symmetric matrices can be obtained from spectral theorem by proper manipulation. Okay, just to calculate this, I think a minus. Okay, in this polynomial, just substitute a and use the fact that a can be written as a equal to u d u transpose, where d is the diagonal matrix. Okay, plug in the polynomial and you can show that. Okay, it's not hard to see. Okay. So now let us come back to the graph part, spectral graph part. We have given a brief overview of the symmetric matrix theory. Now we will use all the facts, whatever we discussed so far. Okay, so I hope you remember what we discussed half an hour back. So G is, we are working with always a connected graph. Okay, so adjacency matrix, its ijth entries or uvth entry is 1 if there is an edge between the vertices u and v. Okay, so certain things are evident. So one is the matrix is a symmetric matrix because we are working with undirected graph. Okay, the second property is you take the sum of 2 by 2 principal minus, that should be equal to the number of edges up to sign. Okay, so E of G stands for the edge set, and this absolute value for E of G denotes the number of edges in the graph G. Okay, how to show this? So principal submatrix, I have given the definition. Okay, so what are the 2 by 2 principal submatrices? So proof of 2, fact number 2. So I have to take the ith row and jth column. Then I have to take the same row, same column, ij, same columns, ij. Okay. So what are the possibilities for the entries? So ith entry, that is just a diagonal entry in the A of G, that is 0, and jjth entry, that is again 0. Because in your graph, the ith entry, the adjacency matrix, ith entry, jjth entry are equal to 0. Okay. Hence, you should add 0 in the diagonals. What about off diagonals? What are the possibilities? Either 0 or 1. So here I will get an 1 if I is adjacent to j. Otherwise, what I will get? 0, 0, 0, 0 if I is not adjacent to j. Okay. So 2 by 2 principal minor. That means I had to calculate the determinant. So determinant here is -1 and determinant here is 0. Okay. So let us go back and see the statement. Sum of the 2 by 2 principal minors of A. Okay. That means if I take sum of all these 2 by 2 possible 2 by 2 principal minors, what I'm going to get? If there is no edge, their contribution is 0. If there is an edge, -1. If you sum everything, I'm going to get the number of edges sitting in the graph, okay, which is multiplied by -1. That's all. This gives the proof of part 2. What about 3? Can we extend this analogy? Or can we extend the same analysis? So let us take I, J, K. These are 3 vertices of the graph, or 3 rows of this matrix A of G, and IJK, the same columns. Okay. So the diagonal entries are fixed already. Only for off diagonal entries you have choices. Okay. How many choices you have, or what are the choices you have? So one possibility is you draw the graph. Okay, IJK, they are sitting inside this graph, inside the graph. Okay. So one possibility is they are mutually non-adjacent. That is, there is no edge between the vertices I, J, K. Okay, you don't have any edge. That means that every entry of this matrix will be equal to 0. So in this case, you are getting determinant 0. Okay, so no edge in this case. No edge between I, j, k. In this case, your determinant is equal to 0. When you have only one edge, what will happen? That is either between the vertices I and j, I have an edge. Then what is happening? Then in this matrix, the row corresponding to this vertex k, that is a 0 row. Okay, so that means that the determinant is equal to 0. That means if you have exactly only one edge, in that case also you are going to get 0. Okay, so symmetrically, if you have edge between I and k, if j is not adjacent to I and k, then the row corresponding to j is equal to 0. Okay, so two edges. Suppose if I have two edges, then what will happen? Let us say I and ij, ik, these are all two edges. Okay, then what will happen in this matrix? Look at the row corresponding to I, j, k. Okay, let us complete this matrix. So I is adjacent to both j and k. Okay, hence I can do this 0, 0. The rows corresponding to j and k are identical. Hence, in this case also, you are going to get determinant equal to 0. Okay. So in general, in a graph, if you have two vertices which are having same set of neighbors, okay. I repeat, in a general graph, if you have a pair of vertices which are having same set of neighbors, then in the adjacency matrix, the rows corresponding to them are always identical. Okay. Hence, the determinant will be 0 in that case. Here, so in this case, we are going to get a 0 determinant for this 3 by 3 principal minor. Okay. Now, what is the left out case? 3 edges. So for the 3 edges case, we already know you are going to get just the complete graph. For the complete graph, you know all the eigenvalues. Using that, you can calculate the determinant. Otherwise, you can just do the calculation. What you will get? Any guess? What's the determinant of this 3 by 3 matrix? That is just 2. Okay. So whenever you have a K3 or you have a complete graph on 3 vertices sitting inside the graph, you are going to get a 3. You are going to get a 2. Okay. This 2 you are getting as a principal minor of the 3 by 3 principal minor. Okay. So let us go back to the statement. What does it say? Sum of the 3 by 3 principal minors of A, okay, that equals to twice the number of triangles. So 3 by 3 minor we have calculated. Out of the 4 possibilities, we have only one non-zero possibility. That one non-zero possibility is also corresponding to a triangle. Given a triangle, I am getting a 2 in the sum. Hence, twice the number of triangles is obtained by the 3 by 3 principal minors. Okay, sum of the 3 by 3 principal minors. So this is also 2. Okay. The next thing is A is a square matrix, so it makes sense to talk about A power k. Okay, A power k, I mean take the powers of the matrix A repeatedly, A square, A cube, and so on. Okay, so that A power, the ijth entry of the matrix A power k, it does have some combinatorial significance. Okay, so it says that the ijth entry of the matrix A power k equals the number of walks of length k from the vertex I to j. Okay, A power k you calculate. Look at the ijth entry of the matrix A power k. That says you the number of walks of length k from the vertex I to j. So we already said what is a walk. Okay, I'll just explain briefly. So A into A, you see, first of all. Okay, I think this is point number 4. What is the ijth entry of A dot A? So this will be summation aik akj, k varies from 1 to n. Okay, this is the ijth entry of your matrices. Okay, so now you see product of two numbers aik akj, both are either 0 or 1. Okay, 0 or 1 numbers. So this will be different from 0 only when aik is different from 0 and akj is different from 0. In other words, the vertex I should be adjacent to k and the vertex k should be adjacent to j. Only in this case we will get a non-zero term inside this summation. Okay. So in other words, this in A square, the ijth entry, if it is different from 0, what does it say? The vertices I and j should have a common neighbor. This is one possibility if I is different from j. Okay. This can be also thought of as a walk of length 2. In this case, it looks like path, but it is only walk. I will explain why it is only walk. Okay. Walk is like you take I equal to j. Then what are you going to get? Then you are going to get I, k. Okay. Go from I to k and come to I. Okay. The diagonal part you will get only walk. Okay. Here what are you getting? From I to j, I have a walk of length 2. Then I'm getting a non-zero entry here. Okay. Corresponding to every non-zero entry, I'm getting a walk of length 2 between the vertices I and j. Okay. Now, for a square, if you can convince yourself, then a square, a power k, this you can think of a power k minus 1 into a. You can do an induction. Assume that a power k minus 1, the ijth entry gives you walks of length k minus 1 from I to j. Then argue that if you take the product, the same idea, same whatever I have written here, use the same logic to conclude that in a power k, the ijth entry will give you number of walks of length k between the vertices I and j. This will be used in many places. Okay. Okay. Proof of 4 is done. Okay. I will try to complete the proof of the 5 and 6, and then I will stop for the morning session. Okay. So if Vi and Vj are two vertices, okay, such that distance between them Vi and Vj is equal to n, then the matrices Ia a square up to a power m, this is a linearly independent set. Okay. Okay. So let me explain. So I'm using linearly independent. So let me explain that. The matrix I, A, and so on, all the powers of the matrix A, you take everything. Okay. So everything I can think of, they are elements of R n by n. Okay. This is an n by n matrix. Okay. These are all n by n matrices. And the n by n matrices, this is a vector space. Okay. R n by n, it is a vector space over R itself. Okay. So the statement says that if distance between the vertices Vi and Vj, okay, let's say if this is equal to some k, then the vertices I, so not the vertices, the matrices I, A up to a power k, this is a linearly independent set. This is a linearly independent set in Rn by n. Okay. How to show this? Suppose you take a linear combination, okay, which is going to give you 0. Suppose this linear combination alpha 1i, alpha 2a, and to alpha, maybe this is k plus 1. Okay, just to careful with the notation, alpha k plus 1. If this is equal to 0, then what I have to show? The claim is alpha equal to 0 for every 1 less than or equal to I less than or equal to k plus 1. This is what I have to show. Okay. How to show this? See, distance between Va and Vj, if you look at this line, what I'm writing, distance between Va and Vj is exactly equal to k. Okay. So that means that the ijth entry of this matrix A power k, this is different from 0 because I have a path of length k from the vertex I to j. Okay. But at the same time, A power k minus 1 ij. Okay. You take 1 power less than k. Okay. A power k minus 1, the ijth entry of this matrix A power k minus 1, this should be equal to 0. Okay. Because if, what is the meaning of this? If A power k minus 1, ijth entry is different from 0, then I have a walk of length k minus 1 from the vertex I to j. Okay. If I have a walk of length k minus 1 between the vertices I and j, then the distance between the vertices I and j should be strictly less than or equal to k minus 1. Because every walk contains a path. Every ij walk contains a ij path. Okay. Hence, in the matrix A power k minus 1, the ijth entry should be equal to 0. In fact, in the matrix A power j, this ijth entry should be equal to 0 for every 1 less than or equal to s less than or equal to k minus 1. All these terms should be different, equal to 0. Okay, maybe you can start with I not equal to j kind of thing. Okay, anyway, distance is k strictly greater than 0 if I take vi is different from vj. So this says that the ijth entry only in A power k that is different from 0. In the rest of the matrices, this is equal to 0. Okay, so this implies, what does it imply? Alpha k plus 1 should be equal to 0. Right? Because if you look at the ijth entry in the entire linear combination, you look at the ijth entry, then the ijth entry is different from 0 only in the matrix A power k. The matrix A power k, the coefficient of the linear combination is the alpha k plus 1. Hence, alpha k plus 1 should be equal to 0 in order to get a 0 in the ijth entry of the right hand side. Okay. So by a similar argument, you can show that like this matrix A power k minus 1 is independent of rest of them, and so on. You can together you extend this argument to show that this all the matrices A up to A power k, this collection is linearly independent. Okay. This has a non-trivial consequence, which Professor Satya also will talk about the similar type of things in the afternoon. Okay. So I have given a proof of 5. So let me give a proof of the 6th one. Okay. So 6th one says that if I have a connected graph, okay, with k distinct eigenvalues, and if the diameter of the graph is g, the diameter is we already defined. So what is the diameter? You measure the distance between any two pairs of vertices VA and VJ. Take the maximum amount. Okay, that is going to give you the diameter. Okay. So diameter of the graph, if it is d, then the number of distinct eigenvalues should be at least d plus 1, or k is strictly greater than d. That's what this says. Okay. So before maybe I had to wind up after completing this proof. The reason to list out all this property in this slide is, so you can see one side of all these statements you see, okay, starting from 2, sum of the 2 by 2 principal minus, sum of the 3 by 3 principal minus, ijth entry of A power k, all these things are matrix theoretic properties. Okay, on the other side you see number of edges, number of triangles, number of walks of length k, everything is a graph theoretical property. So these results are properly connecting the matrices and the graphs. Matrices and graphs. Okay. And here also in the in the 5th statement also, something about the distance between the vertices say something about the linearly independentness of the powers of the adjacency matrix. The last one, it says about something about the number of distinct eigenvalues, connect the number of distinct eigenvalues with the diameter of the graph. Okay, one is a linear algebraic quantity, the other one is a combinatorial quantity. Okay, so let me prove the last one. So what do I have? Diameter of the graph, diameter is equal to d. Okay, so that means that I a up to A power d, okay, this is linearly independent. Okay, so that means that if you take any linear combination alpha 1 I plus up to alpha d plus 1 A power d plus 1 A power d, this is different from 0 for any set of scalars, not all together 0, this is different. Okay, so equivalently, if I take any dth degree polynomial, will not annihilate your A. Or will not be a minimal polynomial for A. Okay, that is degree of the minimal polynomial should be greater than or equal to d plus 1. Any polynomial of degree cannot be satisfied by this matrix. The degree of the minimal polynomial should be d plus 1. Hence, it is a symmetric matrix. We have seen that one of the facts I listed. For a symmetric matrix, your the minimal polynomial is nothing but just take the product of the linear factors obtained from the eigenvalues. That is x minus lambda 1 into x minus lambda 2 into up to x minus lambda k. If it has k distinct eigenvalues, this means that a of g has at least d plus 1 distinct eigenvalues. That is diameter is strictly less than k, where k is the number of distinct eigenvalues. Right? That's what it should have, at least a d plus 1, yeah, distinct eigenvalues. Okay. In other words, d should be less than or equal to k plus 1. Okay. The same expression will show up in Professor Satya's lecture. So he may discuss about the case that when this d will be equal to k plus 1 and so on. Okay. So these are all like a very basic results in spectral graph theory. More precisely about only the adjacency matrices. Okay. So after this, I will discuss something about the Rayleigh quotient, and then this interlacing inequalities, the variational characterization, and how to apply them in graph problems. Okay. Yeah. So, do you have any doubt? If you have any doubt or comments, you can unmute yourself and you can tell. Maybe I can stop recording now.